Hello, everyone. My name is EJ Kreiner. I work for Hawkeye360. I'm a processing engineer. I do a lot of work with GNU Radio and RFNoC. So I'm going to talk a little bit about that today. This is the first of two talks that Hawkeye has here. This one's specific to Polyphase Channelizer, which, well, we'll talk through that. And then the one tomorrow is a more general overview of some of the things that Hawkeye's doing. But just to get started, I'll give you a little bit of introduction to Hawkeye360. So we're a company, we're a venture-backed startup based out of Herndon, Virginia, outside Dulles. We have a really unique technical mission. So our goal is we're launching a constellation of small satellites, and each cluster of small satellites is three satellites. They look kind of like that in the bottom right. They're about the size of two briefcases stacked on top of each other. And they are going to orbit in a polar orbit, so passing everywhere on Earth every day. They're going to collect RF data from 100 megahertz to 15 gigahertz. And they're going to perform TDOA, FDOA measurements, so physical measurements of the received waveform, and perform geolocation, so independently identify and solve the equations, geolocation equations, Kalman filters, to establish where a particular RF emitter was, whether they're cooperative or not. So this is the Hawkeye360 technical mission. And we have a lot of spectrum. So 100 megahertz to 15 gigahertz. We have a couple front ends on our radio, which I'll talk about tomorrow. But we're in space, so in order to actually do anything, we have to collect this data, and as everyone's RF engineers here, you can imagine, it's a lot of data, and we have to figure out how to be able to best handle that. So it's very important to us as from an infrastructure standpoint to be able to channelize spectrum. So if you think about maritime frequencies, like VHF frequencies, you have about 10 megahertz of frequency, and if you have an embedded device, you're probably not going to be able to operate on all 10 megahertz, like 12 to 25 kilohertz channels of 10 megahertz of data at once. So you have to have some way to downsample or process that, or use the FPGA to be able to accelerate some of your processing without the ARM interaction. So very important for us to channelize spectrum. So the title of my talk was improving the RFNoC channelizer. So there's a Edis out-of-tree module that does channelization, and well, we kind of evolved from there. So, well, I'll talk a little bit first about channelization. So what is channelization? Just to introduce the problem, I'm sure most people are aware of this, but if you collect a large contiguous chunk of spectrum, so say 10 megahertz is a good number, maybe 40 or 50 if you're using the 9361. It's a nice round size. You often have subchannels inside that big band of interest that you want to extract. And so you can see that in the little illustration in the middle, or the bottom middle of the screen, you might have different channels throughout your chunk of spectrum, and you really just care about the information in one channel or two channels, or maybe all of them, but you don't necessarily need everything. So the goal of channelization is to take the chunk of spectrum, pull out the relevant channels, and just process on that in like a more optimal way. All right, so there's ways to design a channelizer, and if the channels are evenly spaced, which it happens for a lot of commercial signals, so if you look at the maritime band, you have a bunch of evenly spaced channels, then the Polyphase Channelizer is an efficient implementation, and we want to do that in the FPGA so that we can channelize higher bandwidth and remove some of that processing load from the ARM into something that is parallelizable, something that can run at whatever rate the digitizer can feed us samples without having the processor in the loop. All right. So what's the status of the open source channelizer? I was really hoping that this talk would be improving the one that exists. And so when I started to talk about improving it, there's two specific things that the one that was presented last year was missing. And this is it was a great talk last year, and it ended up in a repo online that that is an RFNoC out of tree module, and parts of it compile and build the IP. But the two things that we're missing, number one, is channel selection. So if you have 40 megahertz of data and you want to channelize it into, say, 128 channels, you can channelize it, but if you still have to take all 128 channels and pull that into the processor, well, you're not really getting any processing. You're not really getting any benefit from that. So that's kind of like low-hanging fruit. And then the second part of this, so that's channel selection and muxing. And the second part of this is timestamping. So, there's a channelizer in GNU Radio. I want to be able to handle timestamping in the RFNoC framework so that you can take timestamps in the FPGA and move them around and do useful things with them. That's really important to us. As you can imagine, we're doing physical measurements, T2A, F2A, so the timing component and propagating that timing is critical. The reality of this, we tried to use it, and simulation's not seems to be broken right now, so something might have gotten lost. Well, that really meant for us, we've just got to do the channelizer part too, instead of just the improvement part. So we're working on that. We'll cover the basics of polyphase channelizers. All right, so let's take a look at the math. I'll just walk you through kind of a quick overview of channelizers. So, I'm sure a lot of you are aware of this, but for those of you that this might be new information, I hope that I can make this accessible to those of you that haven't quite seen it before. So when you look at the math, if you're channelizing something, just fundamentally, you want to do two things. You want to do a frequency shift. So take something that has a frequency offset and put it at like a DC component if you're looking at it in IQ space. And you want to do a low-pass filter because you don't want extra higher-order products mixing in, and you want to do a downsampling. So you have those three operations: of frequency mixing, filtering, and downsampling. And when you look at the math, you can arrange the equation such that you have exactly that. And in this equation here, I'll just point out a couple things. So the h of the n is the low-pass filter. The x of n is your input signal. So this is the full bandwidth waveform that you want to channelize. And then the exponential is the mixing term, so that's your frequency offset. So let's manipulate this equation a little bit. And this is the canonical polyphase implementation. Again, I hope I can make this accessible. You've just taken that summation, exploded that, and reorganized it. And what you'll notice is on the vertical side, each column is a phase of your filter. And what does that mean? I have a thing a couple slides from now. I want to just jump ahead just a second. So a phase of the filter is just as simple as this. So in this diagram, you have four filters plotted vertically here. And if you look at the bottom one, that's a sync filter. That's a sync function. And you can see that the samples are perfectly aligned. And if you go up one, your sample alignment is off by one. So it's still the same filter. If you look at the information that's in that, it's still the same function. It's just sampled at a phase, one sample offset. So that becomes your phase of the polyphase filter. And you go up, and now your samples are equally spaced around the peak. And then you go up again, and you're another sample offset. So these are your four phases that we refer to when it's polyphase. And so you can see your h of n, which is the filter that we're using, on the column here, you go down by increments of this n. So first you start at n, and then you go to, or first you start at, if you look on the left, it's easier. First you start at 0, then you go to n, then you go to n times p, which is the number of taps per phase. Okay. On the vertical side, on the horizontal side, this is just a Fourier transform. So you can see your filters incremented, and then you have an exponential that is increasing. On the very left, you have e to the j 0, which becomes 1. So I don't have the exponential indicated on the left, but this is a DFT on the horizontal spot, and on the vertical spot, this is just a filter because your exponentials are exactly the same. You don't have a frequency offset on this vertical row. So this is the concept of the polyphase filter. You have first just a filter, and then you have an FFT. So if you look at the actual implementation, when you do this, and this is what we've chosen to implement in the implementation we did, you put in your sample stream. The left indicates your full 40 megahertz, or whatever your spectrum is. You mux that to n different filters, where each filter is the same h of n, sampled differently. So you use your different offset tabs. And the output of those filters gets processed into an FFT. And then on the output of that are your different channels interleaved, such that the first channel comes out on the first sample, the second channel comes out on the second sample, and the third channel, and so on. Okay, and then there's the filters again. Okay. For a quick review of the polyphase, so the next question is, what is the group delay? This is how we're going to understand how to handle timestamping. So group delay is actually pretty straightforward. So if you take a step back and just think of the channelization operation as if you take your entire 40 megahertz, or whatever the bandwidth is, first you mix it, and then you apply a filter to it. That's what the math suggests you're doing across all filters. We've manipulated that math to be more efficient for the polyphase implementation, but it's fundamentally the same thing. It's pretty clear that for every channel, you're applying the same filter. So the magic there is that you have the same group delay. And so that means that on the output of your channelized stream, after you've channelized everything, when you have these interleaved n channels, then each sample from all of the different channels will have the same timestamp applied to that. So that's really kind of one of the core insights for how we're going to manipulate timestamps in the FPGA and then also in GNU Radio. Okay, so now let's tie this all together. Actually, how did we do this? How do we change the demuxing and the de-interleaving and the timestamping operation? So we do the channelization in the FPGA. This is what kind of existed as of last year's talk. So one thing to mention, the Channelizer discussion from 2017 that has a paper on it is a little bit different Channelizer implementation. We've implemented it slightly different. It's just a different choice of how you do it. But I think the rest of the stuff still applies. So we have these interleaved channels. We down select which of those channels we want to send back to the host processor. The processor then gets this interleaved stream and then is able to demux that. And it's basically just a de-interleaver from GNU Radio, stock de-interleaver. And the timestamp is then routed to each channel individually. So I'll show a graphic of that. In block diagram form, this kind of demonstrates more of what we're doing. So FPGA, we have the channelizer, which is replaceable or interchangeable with other channelizer implementations. We have that outputs interleaved channels. You have a down selection, which looks at those interleaved n channels and takes only the correct indexes, passes them through a streamer to the processor, and then you have a demuxer, or I guess a muxer on the software. Okay, so how to actually do this timestamping. When you actually look at the implementation and try to do it, it gets a little bit more complicated. So you have to do the tick count, the timestamping in a way that's deterministic when you receive it in software again. So our solution to this was to basically manually format packets. If anyone's used RFNoC, the simple mode approach doesn't apply here. You have to do things a little bit more carefully. And just talking to the graphic in the bottom of the screen here, this shows a demonstration for like 4 channels. Let's say the 0th channel comes out first, 0, 1, 2, 3, but we only want to return channels 1 and 2 out of those 4. then we just simply select the 1, 2, and then from the first output, and then 1 and 2 from the second output, and that forms a new packet. And the other thing you do is you take the timestamp that came in to the RFNoC unit under test, pull that timestamp off, apply that to the very first sample on the cheddar packet, and we know that when we go back up to software and do this deinterleave block, that you take the corresponding channels, put them into their own output streams, and you take the time tag that was on the first sample and duplicate that on all of the others. So it really becomes, in some extent, pretty straightforward how to do that part of it. This is just talking through a little bit about some of the details. We don't need to go through all of this, but it does kind of walk through the algorithm, manipulate t-valid, t-last. The FPGA will do the muxing appropriately. On the end of burst, you need to reset everything because you can't really handle this non-integer offset. One thing that we have a concept for and we're currently working on is also accumulating packets. So let's say you want to channelize 128 or 256 channels, but you only want like 1 or 2 or 3 channels out of that. Then let's accumulate 100 different packets on the input, use that to format one packet on the output, and then pass that along. So that's coming very soon. And then in software, again, this is kind of walking through the algorithm. It's very similar to the deinterleaver, the stock GNU radio deinterleaver, with the caveat that the timestamp is then handled differently. Usually, if you're going to timestamp the output channels, you would take the sample rate, increment that, and then that would be, if you're deinterleaving, you would do the time-advanced sample based on the sample rate, but that's not what we're doing here. You're using the same time tag. So don't forget, though, that when you're downsampling, you have, based on the polyphase channelizer, if you're channelizing, you have a rate change and a frequency offset change. So don't forget about that. And let's just show a few examples of what this looks like. So this is what we've currently been testing. It starts with just a noise source to prototype things, do a frequency translation, pick some channels, and in this implementation, we've got 8 channels implemented, 8 channels deinterleaved. So just look at everything, make sure things are working. There's an example of some of the parameters that we need for the channelizer, and but you could also do something different where you only return 4 channels and then you deinterleave. You have 8 total streams, for example, but then you only output 4 of them. So that kind of shows the prototype approach for how you would return everything as one stream and then push that onward. So on the output side, we see it channelized properly. There's something going on at DC frequency that we need to address. We'll look at that. Okay, so now I want to pause a second because the channelization and the timestamping is actually fairly straightforward. So what are a few lessons that we learned from the RFNoC GNU radio infrastructure cohesion that actually supports this? Well, first, with the EDIS devices, and you try and if you usually try and stream something, you get a time tag, frequency, sample rate. And by default, you don't have that on the RFNoC blocks. So first thing, you need to do that. So we have some hooks to be able to do that. It's not really cohesive with the overall RFNoC infrastructure. So I think that's one thing I want to start a discussion on, is how we improve that. The second part is that when we're developing this, or anything related to timing, the infrastructure would be, we really want to be able to take a file meta source that we've recorded from our USERP in the lab, and now we have like a golden reference file that has a timestamp associated with it. We want to take that file that has an item tag saying the exact time, and then we want to be able to run that through our RFNoC flow graph, just basically stimulating the result as though we were attached to a real radio. Well, You also need a way to take those item tags from the input stream and then translate that into a metadata that gets passed to RFNoC. And again, we've got something that is not part of the cohesive RFNoC framework that does that, but it's something that you need to do. Another thing that's important to think about is, the third thing here is RFNoC blocks. If you're interested in doing things that are timing related, you need to think about the ticks per sample. So this is another infrastructure update that we need to think about is, like for example, if you receive on the radio outputs samples where one sample represents one tick of the master clock rate. And then let's say you use a DDC operation and you downsample by 8 or 6 or whatever it may be. Now on the output of the DDC, you have a different number of ticks per sample because you've downsampled. So it's now all of a sudden 8 ticks per sample, and you want to give that to some other FPGA processing block downstream. And if that processing block downstream assumes that there's a single tick per sample, and you try and do time critical work with that, well, that's an infrastructure thing that's going to be wrong. You need to know like what the amount of ticks per sample it is. In this example, it's 8, but it could be anything. There's ways you could do it. Like for example, if you look at the timestamp of one packet and then look at the timestamp of another, and then subtract and divide by the number of samples. I mean, maybe you could do that, but I think there's probably a better way to do that. And in our approach is just to tell it, say, okay, that you know exactly what the number of ticks per samples is. Okay, what's left to do? There's a lot left to do. I've identified a couple of problems already throughout the talk that we're going to be working on. But there's a lot more places that this can go. So, well, an obvious one, right now we've just prototyped it with a fixed number of channels. We want to be able to reconfigure that. Go, 8, 16, all the way up to 256 or 1024 channels, N channels. That's probably pretty low-hanging fruit. Then we'll start to get a little bit more advanced, a little bit less low-hanging fruit. So instead of taking one stream from RFNoC back to software that's then deinterleaved, one thing we could do is pull the demuxing operation into the software handler for the RFNoC block. So that would involve overriding the general work. We could do that. The next thing that's a step beyond the software change of overriding the general work function to demux samples would be to repacketize samples inside the FPGA compute engine, create packets that are all a single channel, and then route that to some other downstream RFNoC block. That would be almost the holy grail. That would be really great. And I've illustrated that on the top right here, so showing a flow graph representation of the channelizer going. I've got 2 channels going to file sync, and then I've got 1 channel going to some other RFNoC block. In this case, I just threw down a DDC for example purposes, but could be anything. Could be like a timing recovery, like demodulator, whatever that may be. Okay, and then, all right, what's the next step beyond that? So if you're doing a channelizer, there's also this concept of, well, first you can channelize into n equally spaced channels. You can also take adjacent channels and reconstruct larger bandwidths. So that is going to be absolutely critical if you have like a spectrum where you have things that are different bandwidths. I mean, look at ISM, for example. You've got something that's megahertz and then something that's a lot smaller. Just so many examples of where the polyphase reconstruction would be useful in terms of receiving signals dynamically in the FPGA. Okay. All right, so where do we want to go with this from here? Basically, so just to summarize, I really want to revive this channelizer. I think it's a really critical piece of infrastructure. We've prototyped this channel down selection, shown that it works. We've implemented the timestamping, the channel muxing. We've been able to, in simulation and file input and output through the RFNoC blocks, confirm that the timestamp propagation, the theory of the similar group delays is actually accurate and empirically correct, which is always good to confirm that theory is accurate. But like we said, there's more places to go. There's work on our end to clean some stuff up. It's not publicly released yet, so I'll preempt that question. I'm going to work on getting that released, and I really want this to be a utility that's available for the general RFNoC community of software developers and FPGA developers. And in order to do that, I would really love to engage with anyone here that has similar ambitions and would want to contribute and help look at some of this future work, help debug, help put more eyes on this, because if I can show larger community buy-in, then it's a lot more compelling offer to be able to look at something like this as a utility as opposed to some critical piece of IP, which I really think it's a utility that everyone should have if you're doing FPGA work. So thank you.
We have time for questions.
I saw one in the back there too.
Yeah. What are the clock requirements to achieve this? Like, do you have any? Is it all in one clock domain that you have to achieve this, or?
Yes, we're doing it in one clock domain. Okay. Yeah.
Really interesting stuff. The polyphase approach is very general. It's not just for this one channelizer problem, right? You can implement filters in it. You can use that for clock recovery. Do you have any intentions of taking those types of more general approaches and trying to put them in RFNoC? You could take the guts of what you did and maybe use it for polyphase clock sync or even just a FIR filter. That'd be great. It'd be a really efficient implementation on the FPGA.
Yes, I would love to do that. I think that's the short answer, yeah. Oh, I also want to mention, too, that this work was mostly done by my colleague, Tim Kerp, who couldn't make it this week, so I do the presentation for him. So, yeah.
There was one more on this side, I believe.
Oh, yes.
Yeah, is there a amount of bandwidth that you're overlapping your channelization filters?
Yeah,
and is there a kind of like I assume you're going to need longer filters to have less overlap. Is there a sweet spot in using FPGA resources?
Yeah, so that kind of ties in with the last question a little bit. There's lots of different implementations for things you can do with polyphase, and like the one presented last year, the output of each channel is a 2x oversampling of the channel. So what you can do is have a little bit tighter filters that go like actually use the entire bandwidth of the channel that you're trying to pull out. The one we implemented for our prototype purposes is a one critically sampled representation of your channel. So if your channel's 1 megahertz, you have 1 megahertz of samples. But I really also want to support so the paradigm that you're talking about.
Any more questions?
Yeah, over here. Good presentation, thanks. You talked about wanting to get this a bit more mainline in RFNoC. Where does it stop? How do you make a piece of IP like this generic enough that it'll meet everyone's needs, but specific enough to meet your needs? Is 40 megahertz of bandwidth, channelizing 40 megahertz of bandwidth? Is it 100, 160? Where does that stop to when you go, oh, if I'm up at 160, maybe now I need to run it multiple samples per cycle?
Yeah, right.
And so how do you make that generic enough that it will be extendable for the future?
So for a large part, I'm developing with COTS hardware. So the 9361 that's generally available in E310s and that sort of thing. And so where does it stop? Oh, geez, I don't know. I mean, if the RF, I'll see the Hedgehog presentation later. Maybe we expand this to multiple gigahertz of spectrum. I would love to see that too. But yeah, I don't really have a great answer for that because to some extent, you have to design to your application. Like if you have 2 megahertz of spectrum, it's not going to apply. You just won't be able to run it serially in this particular application. But I would hope that that you can use a similar framework. I don't think there's a great answer to that. That's one of the problems we face.
The signals that you're TDOAing, let's say you're doing, radar or something where it's a very wide band are you assuming your signals are falling within one channel, or can the signal span multiple channels? You can throw most of those out except for the beginning and the end and still get a fix on a wideband signal?
Yeah, that's where polyphase reconstruction is going to be useful, is being able to pull out channels or larger channels that span multiple smaller channels. To start, I probably wouldn't use it on something like radar, which can be 40 megahertz wide. I would try to use it on the things that are small channels inside of, say, 10 to 20 megahertz, like SATCOM phones. You have a plethora of channels available. Let's pull those out and do some useful work on this.
I think we have time for one more question.
So maybe you already mentioned this. So how many taps in the implementation that?
Oh, I don't recall. I don't recall that answer. I can look for that one. I don't know the actual number.
All right, let's thank our speakers.